εδώ δουλεύει, επομένως το αφήνω αυτό εδώ πέρα και το στρέφω εκεί μπροστά εσένα.
Δουλεύει. Απλώς έλεγα μήπως το έκανα χωρίς. Γίνεται το WebEx θα παίρνει έτσι κι αλλιώς. Οπότε από την κάμερα, οπότε είναι άσχετο με το μικρόφωνο, οπότε μπορεί απλώς να φωνάζω. Εντάξει, ευχαριστώ. Λουκές Γερακόπουλος. Ως ου. Έχω κλείσει 10 χρόνια. 3 χρόνια Γερμανία, 13 χρόνια και τώρα λέω κάπως να γυρίσω. Να τελειώσω κάποια project που έχω στην Πράγα ακόμα. Ήταν, εντάξει, η γυναίκα μου δεν άτυχε, τα παιδιά μας είναι Ελληνίδα, οπότε δεν μαθαίνανε ελληνικά, είναι φιλοσοφία. Λέμε τώρα θα κάτσουμε, μάλλον δεν θα κάτσουμε, οπότε πρέπει να φύγουμε πριν πάνε για... Κάποια στιγμή πρέπει να το πάρεις απόφαση. Εντάξει, εκτός άλλους μόνιμος είναι εκεί, οπότε... Εντάξει, η πίεση είναι η οικογένεια πλέον. Πότε ακριβώς είναι περισσότερο το πότε. Από άλλες χρονιές φέτος που κάνουν 5 μέρες, αλλά έχει και πολύ ενδιαφέρον. Ναι, προφανώς. Ναι. Και εντάξει, θα κουράσει, τι να γίνει. Αλλά... ξεκουράστη με γιορτές. Όχι, είναι μεγάλη συνεισφορά. Είναι η κατάλληλη περίοδος, γιατί έρχονται και όλα τα παιδιά από έξω. Ακριβώς, το καλοκαίρι δεν ξέρεις πότε θα έρθει ένας πότε άλλος. Τώρα είναι, ας πούμε, με frame of reference και χωρικά και χρονικά. Ακριβώς, είναι το σωστό. Όχι, είναι το perfect time. Βολεύει να ξοδέψουν τελευταία χρήματα από το budget.
Γιώργο, συγγνώμη, αυτό είναι το... δεν ξέρω, αυτό είναι ή όχι.
Κάπου λέει boats.
Αυτό δεν είναι το... είναι αυτό το...
Ναι.
Αυτό το Kingston εδώ πέρα.
Ναι, ναι. Τι, κάνε τι. Είναι σκέτο file.
Α, σκέτο file.
Ναι. Boats ή λεοντάρι στο τέλος.
Αυτό εδώ. Αυτό εδώ, έτσι.
Και εδώ αφήξεις κι
είναι κυρίως αστρονομία, αλληγραμμικά, το ολοκλήρωμα.
Εγώ κερδίσα αυτό, ήσουν άλλες 4.
Δεν έκανε.
Οπότε ετοίμασα κάτι στα γρήγορα.
Okay, welcome everyone to our last session for this workshop, and it's a pleasure to have Giorgos Lukis Gerakopoulos from the Czech Academy of Sciences, who will talk to us about extreme mass ratio in spirals, theoretical expectations and challenges. Giorgos,
so thank you for accepting a more astronomical institute than the main concept of this conference. And extreme mass ratio in spirals are basically a more fancy celestial system than we have we studied in the past, in the last 400 years. So instead of sun, we have a supermassive black hole, and instead of planets, we have stellar compact objects like neutron stars or black holes. And with respect to that, I would like to tell a story to start with. So we will go to early 1600s. There is Tycho Brahe. He got a good grant from Rudolf II, the Holy Roman Emperor, and now he can do his observation in Prague. He has a lot of money, he has observation, he needs somebody from the theoretical department to do the calculations. So he opens a postdoc position. In this call, he accepts Johannes Kepler, who comes to Prague. And now you have to understand the contrast. So Tycho Brahe is a person larger than life. He's partying, consuming a lot of wine. He's very life person. While on the other hand, Kepler is a monk. So the first probably contact was not the best. And Tycho Brahe is a little bit skeptical to give him the data. So you're at your postdoc position, you don't have data, you have nothing to do. Luckily for you, but not for Tycho, he has again a party, and unfortunately he dies. And then after a while, Kepler gets his data and is able to publish two good publications. One, the first Kepler law, and the second Kepler law. I think the most significant is the first Kepler law, because Kepler is a monk. He believes in the mind of God, and the mind of God is perfect. You have to have these perfect spheres on which the planet moves, and suddenly you see the data, and this data cannot fit your, let's say, your ideas about what's perfection. So you have to reduce, and this is the biggest for me thing that Kepler did. He basically said, okay, this is the reality, I have to accept it, and I have to give up what I think about nature. And he accepts that it's not even circular, it's elliptical, the motion of the planets. So basically the story of extreme mass ratio in spiral is about, I will refer to that quite often. So, I will give an introduction, why extreme mass ratio in spirals are interesting, what we want to do with them. And we'll start with gravitational wave detectors. So what are gravitational waves? They are perturbation of the space-times, of the fabric of the space-time. And I will give an analogy. It's like having a calm lake, and then you come and throw inside the lake a stone. And then the waves come to you, and you have to measure the waves, and said not only that a stone was thrown in it, but what was the shape of the stone. So it is something like that. We get the strains, We don't know anything about the system, but we have to somehow simulate it. So what we do, we have different models. I will speak about that later on. But now I would like to speak a little bit about our observatories. So these are the terrestrial. The existing one is LIGO. You know about the detection. It's measuring basically stellar or intermediate, I would say, intermediate mass ratio, not mass ratio, intermediate mass black holes, mergers. So as we go to the left-hand side, the merger of the frequency at which the merger happens is going proportionally to the mass of the proportion. As we reduce the frequency, the mass basically grows. It doesn't matter if you have a small black hole orbiting around a supermassive, or you have two supermassive black holes. It's irrelevant since you have two supermassive, let's say 10 to the 6. You add them, you have, again, something 10 to the 6. You have small, stellar, 10 to the 2, and something 10 to the 6, again, it's 10 to the 6. So basically, here we have just black hole binaries. And what we do currently is that we have to produce waveforms. I will show later on one of them. And we have to do a match filtering. What is match filtering? It's basically, I will take again an analogy. You have Fourier analysis of a time series, and you want to find a frequency. Once you find the correct frequency, you have a peak. It's analogous. So you have different patterns, and you want to fit them to your signal. And when you succeed, you have the best correlation. It's done by Bayesian statistics. I won't go to the details. Now, our current problem is that we have noise, and the signal is buried in the noise. In the future, this will be a different problem. So you have this Einstein telescope or cosmic explorer. There will be in 2035, probably Einstein telescope will be the first. We will have not detections 3 every week. So you will have, as we have during the 04 run, you will have almost every minute a detection. And okay, you have binary black holes that are relatively short of the second, of the order of the second, but if you have neutron star, it will be longer. And then you have overlapses. So now, the problem is not that I have to get the signal out of the noise. The problem is that I will have already overlapping signals. And now you have a barrier which is here, which are the terrestrial, the barrier that the terrestrial observatories meet. And this is the seismic signal from the Earth. And we cannot go below it. So if we want to go to smaller frequency, we have to go to space. So the SIGO is basically a decihertz observatory, space based. And then we have LISA. LISA is a ESA flagship. It's supposed to fly in 2035. Officially and unofficially, we already know that it will be already probably 2 years later, around 2037. And now you have even more problematic setup. You have many sources. You have supermassive black hole merging. You have galactic binary. So all the white dwarf binaries, black hole binaries, neutron star binaries will be so many in our galaxy that it will create basically a stochastic noise background. And they are, if you imagine that they are near to us, so their signal is strong. And then you have the extreme mass ratio in spirals, when you have a small stellar body orbiting around the supermassive black hole. This is the quietest of all of the signals. And you will get all the signals at the same time. So it's like having a lively room where everybody discusses. Somebody's shouting from the one side to the other, and I'm starting to whisper to Yorgos. And you want to hear what I'm saying to Yorgos. It's almost impossible. So what are the strategies that we have to follow? One idea is that we'll start peeling off. We have our match filtering, we'll find the supermassive black holes, mergers, we'll get them off. What remains? Galactic binaries, get them off. And then at the bottom of the barrel, you will find the extreme mass ratio spirals. After all the peeling, and this is not, this is very hard, actually. The other idea that we have is that we put everything together, we call it cocktail. So you put all the waveforms together, you create a super waveform something, and then you say, okay, I have all these binaries that are happening at the same time, what of the cocktails fit them best? So, and always the extreme mass ratio are at the bottom of the barrel, so it's very faint. Except if it's local, so if it's from our galaxy, we'll call them golden extreme mass ratio spirals. They are the strongest, or somewhere in the near, in our neighborhood, Andromeda, or something like that. So, it's already challenging to detect them. So let's see what other challenges we have. So, as I said, you have supermassive black hole, around it you have a stellar object, the mass ratio is below 10 to minus 4, and what you want to do, you want to have, you have basically an orbiting object that is dissipating to the gravitation-radiation reaction, losing energy, angular momentum, and you want to create a waveform. And this, the cycles that this object will make around the central object is around of the order of the mass ratio. So if it's 10 to minus 4, the mass ratio, you have to have 10 to 4 cycles. And this will last in your LISA band around a year, month, of the order of that. So, and one thing that I will comment later, and you have to be accurate up to a degree. If you are, if your precision is greater than 1 degree, you probably will make the detection, but you won't be able to do the parameter analysis to tell what are the masses of the primary and the secondary, what are the spins, how they are aligned, or what is if something funny happening in during the spiral. So, as I said, extreme mass ratio spirals are very interesting because they are scanning basically the background space-time. And you can imagine that if you're so accurate, you basically can tell if this background is square or not, and measure any deviation from general relativity. So this is what the extreme mass ratio are promising theoretically. So we want to confirm that up to good approximation of the central object is a square object, and secondary, or another second thing that we want to see if that what we predict theoretically from GR actually holds. And then there is also the rate issue. So currently we don't know, the population models tell us that we might have 1 event during the LISA operation, which is 3 years, it might be extended to 10, but basically calculate 3 years. So it might be 1 to 1,000. So if you detect them from the astrophysical point of view, you can tell something about your population models. And also during your preparation for, while you're doing this modeling of the extreme mass ratio in spirals, you're creating tools in the perturbation theory that can be probably used in other fields. So, modeling in a nutshell. So, the most precise thing that solving Einstein equation is the numerical relativity. We take the Einstein equation, we do 3 plus 1, decomposition, and now we lose what we like about Einstein field equation. They are not anymore covariant. They depend on lapses, shifts. It depends on your coordinate system. But this is the best thing that we can do. So we cannot solve the covariant, so we solve the 3+1 decomposition. And we cannot go all the way away from that. So you see this that ends around 10 to the 3. And basically, the 10 to the 3 is if your postdoc or PhD student forgot to set correctly the parameters, that does a mistake, or she does a mistake, and then you have a run that is inaccurate, but this is unique because nobody does it because it's inaccurate. The best thing that has been done until now, the state of the art that has some accuracies than 10 to the 2. So you see here, the big mass is in the numerator, and the small mass in the denominator is the inverse. And then here you have the distance from the center of the mass of the system. So what you can do to this direction, you can use perturbation theory. It's gravitational separation.
What does it fail, the numerical GR, after this log thing becoming 3? Why do numericals fail?
Your numerical schemes cannot keep up. It's too computationally costly, and you don't have, so you can use something like adapt mesh refinement. So go to small cases, but you have you have a slow and you have a fast time scale. And this creates a problem in order to solve efficiently the Einstein equation numerically. So it's basically having too many scales in your problem. So you have to turn to the perturbation theories, which is basically gravitational surf force, or you can imagine Tarkovsky equation. And now you have the small body orbiting around the big body, and you say, okay, this is very small, so I can use it as perturbation. And this is, again, this is not solving the Einstein field equation. This is somehow a dirty work that you have to do in order to get the result. Or you can go far away from the center of the mass, and now you can compute all the mass ratio that you can imagine, but your perturbations around it's with respect to the velocity, speed of light ratio. And all these are perturbations, so you say, okay, we are used to do perturbation theory, this is solid. What's the problem? But all these are very slow. They're extremely slow. If you want to do the detection, you cannot wait for even minutes. You have to do it in milliseconds. So what you do, you use the effective one-body approximation, which is basically taking the two-body system, mapping it to a one-body system moving in effective potential. And in order to do that, you basically reshuffle the post-Newtonian equations. And you would say, okay, you see the question mark here. It's from Leor Barak 8 years ago. But you have a body moving in effective potential, so the most natural is the extreme mass ratio is parallel. But there is the necessity. Actually, my PhD student is doing it right now, and she's the first that tries to tackle this. Because everybody is focused on this regime, which is the most urgent. We are detecting now, we need models. So you have also urgency tackling in the whole problem. So let us discuss a basic.
Why was the question mark in the self force?
Because here, what you're doing, you're reshuffling it and you're matching it with the numerical relativity. You have some free parameters in the phenomenological model, and now you say the only accurate thing I have is numerical relativity. I start from post-Newtonian, so exactly, you have free parameters and you try to fit it. So it's a fitting problem, basically. and you try to fit it from the two sides, from the extreme mass ratio and the symmetric mass ratio, which is basically when you have equal masses. And again, you're fitting to a theory. You're not really to the, so this is, again, a question mark. So we have basically a small body orbiting a big one, losing slowly energy angular momentum, and it goes, it follows almost geodesic as is dragged into the primary black hole. And since the background is scarce, it's integrable. The geodesic motion is integrable. So the whole evolution happens on an integrable background. And this is good because it helps us to solve some things like the Tarkovsky equation when you want to do the, I will show it later on, when you want to do to solve them in the frequency domain, you have to know the frequencies of your system. So let's see a more accurate. You have an unknown metric. This is G mu nu tilde, and because it's a kerr plus a secondary object that is deforming the space-time background. So what you do in the gravitational shell force, you expand in the mass ratio. So this is the basic idea. And then you have the different corrections of your space-time background. This is the first order, second order. And this is very hard, extremely hard. If you think that we have the Schwarzschild case, circular motion around Schwarzschild, it happened in the late 2000, and we have to wait almost 10 years or more than 10 years in order to get all this term. And now we need also some parts of this. And this started a couple of years ago. So 2035 is approaching, and we have to tackle second order terms, which are not very easy to get. So another approach, which probably will give us detection but not good parameter estimation, is to use another idea. I said before that we have a fast motion, which is the orbital motion, and we have the slow motion, which is the dissipation of energy angular momentum. You can forget, you can average out the fast, and you can just solve the slow one. And this is basically by expressing your system in action angle variables, dissipating your actions, and disregarding all the angles in your system. But this is also slow, the solving exactly. So what we do is using the 2-time scale approximation and say, okay, what we have to do, we have to find the fluxes. We find the fluxes of the energy angular momentum Carter constant. We can dissipate the whole system just by using these fluxes of this constant. And then we have our spirals. And this is basically what we do by solving the Tarkovsky equation. This is a second order partial differential operator. And this is the stress energy tensor describing basically your particle. Now, if you want to go fast, as I said, we have, this is the first order surface averaged, the dissipative part of it. We want to find also the second order part. So this is quite difficult because you don't want to mess up with this part, which is the homogeneous part of your solution, because this is separable. And if you break the separability, it will be very messy to solve it. Even in this is quite, it's computationally, it has a very large computational cost. So one idea is to push the second order term to the stress energy tensor. And now this is a second order, basically, Tarkovsky equations. And in the same, it's basically grabbing that in our group we said, okay, this is a good idea, but what if you have matter? You don't want to mess with this, you want to remain care, so push it to the stress energy tensor. And the first results will be probably published in a couple of months regarding that. So this is another challenge. When you have matter, because matter around supermassive black holes exists, and you have to take care of it and see if it contributes or not. Because you have a multi-parametric system, you have the orientations of the spins, the mass of the spins, the orbital parameters, which is semilatus rectum, eccentricity, and inclination. You have too many parameters. So it's important to see if we have to increase the number of parameters, which we, again, will cause computationally, or we can keep it as it is, a vacuum solution, basically. S is basically from the care, it is the weight of the function. Spin. Yeah. And this is for gravitons, if you like. Yeah. So basically, you again take, you again imagine as a perturbation. You have the mass of the accretion matter with respect to the mass of the primary black hole. So you don't want to do the left hand because you want to keep it separable. And then you...
But the left-hand side comes from diagonalizing complicated systems.
Exactly. You don't want to mess up with that.
Or once you have something else,
exactly. Okay, it's not
diagonalize unless it's a small perturbation.
It's a small perturbation. And this is what you want to do. A small perturbation, because the mass, something like 10 to minus 3, 10 to minus 4 is the worst case scenario. It's very small.
This is the accretion.
Accretion disk.
And that's the mass, the total mass you say is small.
It's small.
Very big black hole with relatively small
and even if it's big, again, it will be very small with respect to the primary black hole, the mass of the accretion, of the accreting matter. So it's again a perturbation thing. So, okay. So we have the phases, which are the most important one. If we lose the phase below, if we go above a degree of precision, we basically cannot do parameter estimation, and we split in 3 parts. This is the adiabatic part, this is the main part, which is taking care of the Tarkovsky equation, the fluxes. Then you have the resonance part, which is basically this square of the epsilon comes from your perturbation. So I said we have integrable system. If you include any perturbation, that's even the conservative part of the cell force breaks the integrability, or you include the spin of the secondary, which again breaks the integrability. You have from one single, let's say, smooth tori in your phase space, you're creating a wide thing that is basically in its, if you want to topologically, is equivalent to a pendulum of phase space. So it grows in width. It's not just zero probability to hit it. It becomes something that is of the order of Punnett square of the perturbation of the width of it. So in our group, we're focusing on the resonance and some parts of the post-adiabatic, which is the secondary spin. And this is very messy. Then you have the conservative part of the cell force. You have this osculating dissipative part of the cell force. You have the average second order dissipative part of the cell force, and probably any accreting matter or whatever it comes to that post-adiabatic term, which is of order of 1. So this is of order of the inverse of the mass ratio. It's 10 to minus 4 the mass ratio. You have 10 to the 4th, while this is very small. So if something funny happens, it will be, funny, departing from general relativity, it will be coming from the resonance part or from the adiabatic part. So GR is not the proper solution to solve the gravitational radiation. And yeah, so I have to. So let us give some example. you have a Schwarzschild waveform and overlap the superposition. So what we have proposed is the Schwarzschild plus some accreting matter, and then we get a waveform from that. And you see the generic motion that you have with inclination. You have some accreting disk around it, and then you have some phase shift that will influence the whole thing. Now the resonances. The resonances, you can use something like the secondary spin. You can see how it grows, find the epsilon and see how important your resonant part of the phase is. And this should be very small. So what we will expect is that if you have, for example, a quadruple deformation of the Kerr metric, then there will be more dominant. This is linear, basically. And it can create something that you were not expecting to see in a standard Kerr spacetime. And what will happen when we cross the resonance? So the frequency ratio will be stable. So we approach the resonance, we cross it, and then we go away from it. These oscillations due to numerical, let's say, insufficiency. In more recent papers, we have fixed that. It's actually a plateau. And if you go to the periodogram, I'm finishing, then you will see, this is recent work from Kyriakos Zestounis, Kostas Kokotas, you will see such a jump in your periodogram. And this is the sign of the resonance. So I will leave the summary probably, flash the references, and tell you something about Tycho Brahe and Kepler again. So you go to the Castle of Prague, you go to the west of the Castle of Prague, you will find these two guys next to each other. I don't know if they want to be next to each other, but they are. And the second thing is that you like to see some historical things, and you go to the Old Town Square of Prague. There is a church where Tycho Brahe is buried. So thank you for your attention.
Thank you, Yorgos. Do we have any questions? Go ahead, Costa.
Is it easy to tell us about the hierarchy of scales in this problem that you're facing?
Hierarchy of scales, you have different, so one is the mass ratio.
Sorry?
The mass ratio of the system. You have a binary system that starts, you have binary systems that have equal mass, and then one is smaller. This is one hierarchy.
So the one you have here is smaller, you have a...
This is basically when we have a small mass ratio.
Okay.
The other one is, again, perturbation theory. You can do, when you have the hierarchy with respect to the velocity of the system. So you have post-Newtonian expansions. And this is two hierarchies, velocity and mass ratio.
Not in general, in your approach.
In my approach, basically you have one scale. It's the slow motion. It's the dissipation of the energy angular momentum, which is slow. And you go to catch that. So you have just one scale. You're averaging out the past, because all these fluxes are averaged over the orbital phase.
Maybe if there is one more question, so that we are not late.
Thanks for the nice talk. So you mentioned a little bit about this, but okay, let me make sure. So if you consider mass, right, not compact offset, but distribution of mass, how this can affect the spectrum, the gravitational wave?
Then it's not spectrum, it's the waveform.
Yes.
So it's the phasing it. So it's it's how much matter do you have.
Right.
So the greater the matter, the greater the dephasing.
Right. And of course, the system does not discriminate between baryonic or drachmatic. It's the same for everything.
Okay, let's thank Yorgo again. And you are welcome to ask more questions also at the end of the session, in the interest of time. So it's a pleasure to have Dimitris Katsinis. Next speaker is Dimitris Katsinis from the University of Athens, who will talk about entanglement entropy of scalar fields in the Sitter space. Go ahead.
Okay, I would like to thank the organizer for giving me the opportunity to present my work here, and of course congratulate them for organizing this nice workshop. So I'll be talking about the entanglement entropy of scalar fields in the Sitter space. And basically what we are interested in is mostly quantum long-range effects that could be imprinted in the entanglement entropy of the scalar fields. So basically this talk is mostly based in these two last publications, but these publications rely on the results of many previous works of a group. So basically, what's entanglement entropy? You have a system A, you consider another subsystem A complement. Both of them constitute an overall system, and you assume that this is described by some density matrix R. Then you trace over the degrees of freedom of the environment, you get a reduced density matrix, and then this reduced density matrix actually describes everything when it comes to the subsystem under consideration. So if you want to calculate something for the system A, you have to trace the operators or whatever you want with this reduced density matrix. So entanglement entropy is just the von Neumann entropy per reduced density matrix, and when the overall system is in a pure state, so you don't have the density matrix is actually psi bar ket psi, then the entanglement entropy is a measure of quantum correlations, and moreover, if you consider a system and the complementary system, then this system have the same entanglement entropy. Now, if you have a system that has finite dimensional Hilbert space, and you have finite many degrees of freedom, then entanglement entropy is finite, everything is very, very well posed, there are no ambiguities at anything, and the entanglement entropy of the system is actually bounded by this value over here. Now, when someone goes into field theory, then because of the entanglement of the short range degree of freedom, when one considers a vacuum state, it turns out that the entanglement entropy is divergent, and the divergence is the most singular part of the divergence is proportional to the area of the system. And when one is in an odd number of spatial dimensions, one has this logarithmic term, and the coefficient of this logarithmic term is universal in the sense that when you scale the cutoff, the number here doesn't change. And when one has even number of dimensions, then you scale the cutoff, and this blue term here doesn't change. So how does one calculate entanglement entropy? Usually people rely on the replica trait. The replica trait actually says that you have to calculate the traces of powers of the reduced density matrix, assume that you get a nice formula that's analytic in N, and take this limit in order to get the entanglement entropy. And basically you can actually think of this as gluing many copies of the system, hence the name replica. It turns out that in two dimensions you can get very generic results that hold for any CFT. And it turns out that the entanglement entropy is given by the central charge over 3 or 6, depending if your system has one boundary, which is common with the environment, or two boundaries. And the result diverges logarithmically. In some cases, when you have holographic theories, you can rely on holography and calculate using the so-called Ruta-Catanaki conjecture. And the most primitive and brute force thing to do is just to take the definitions and apply the definitions and calculate. Usually people don't do this thing over here because for most of the times it's impossible to do it analytically, and you have to do it numerically, and it gets very, very messy. Depends. I mean, usually one assumes that the replica tree works. I don't know. No, so we will mostly use the definitions, and in order to do so, we have to have a quantum mechanical system where we don't have a UV divergence and this kind of stuff.
So in principle, you can apply this to any case, like considering any state. But in practice, you can even consider a pair of oscillators and just operate with a rising operator of one of the two modes. So you have the first excited state, and then you can calculate analytically the entanglement entropy even of two oscillators. So basically, this method works in practice for Gaussian states. Gaussian states, I mean, I'm talking about the vacuum, coherent states, and squeeze states. So, one other very positive thing about this method is that when you calculate entanglement entropy, you actually calculate also the spectrum of the reduced density matrix. So you have much more information than just rather than entanglement entropy. We don't have to weak rotate, so we use real time. As I already told you, this method is more suitable for numerical calculations, but in order to get predictions for a continuous theory, you have to analyze and perform many numerical calculations. And sometimes you can even get analytic results by going back to the continuum limit of the numerical expressions that are discrete. So I will talk a little bit about entanglement in flat space, then I will go on to the de Sitter space, and then I will present the analysis and some results. So how does it work in flat space? Subsystem A are the degrees of freedom inside the spatial region. Then complementary system obviously are the degrees of freedom outside this region. And these two regions are separated by some surface. You have a scalar field. Actually, the easiest thing to do is to consider a spherical entanglement surface because it's smooth. And it's actually easier to do a calculation, and it's actually more relevant because you don't have many complications. And you expand the scalar field in the modes. So basically, you have a theory that's effectively two-dimensional. You have time and the radial coordinate. In order to perform numerical calculations, you have to put the system in a box. And you consider that a lattice consisting of n points. The R cutoff is defined like that. And you define the modes and the momenta like that. So system A are the first n sides of the lattice. And the complementary system is from n plus 1 to n capital N. Now, what's kind of tricky when you try to fit curves is that by definition you want the entanglement surface to lie between degrees of freedom. So when you discretize, you actually consider that the entanglement surface lies literally between the side n and n plus 1. So you consider that when you perform fit that the variable is n plus 1/2 in order to avoid spurious terms that mess the expansions. So discretizing the theory, one ends up with a Hamiltonian that looks like that. What's important here is that this Hamiltonian does not depend on the magnetic quantum number M. And moreover, the various sectors of different angular momentum L do not interact with each other. So essentially you end up with infinite decoupled problems.
Go back before discretization, before discretizing, the actual Hamiltonian.
It's just a free field.
Just a free field.
Yeah.
Okay. And it's in 4 dimensions, but you reduce it to 2D problem.
Yeah, because you spherical symmetry.
Okay.
And this is kind of important part, the thing of the calculation, because you just extract the radial dimension. So if you go to high enough dimensions, regularizing just the angular momentum doesn't help you get a finite result. And actually, if you try to sum the contribution of the angular momentum of the entanglement entropy of all different angular momentum sectors, then the sum does not converge. Because you have some dimensions that are continuous, and you discretize just one. So you have to, in this case, you have to discretize it differently in order to get a finite answer. Actually, I converge the sum to be more precise. So actually, what one does is you calculate the entanglement entropy corresponding to one of the values of L. You get this SL. You go to the other values and so on and so forth. And you actually have to some infinite many angular momenta, then in practice you have to actually impose some sharp cutoff and then try to see how does the thing scale with a cutoff in order to get this value. So discretizing the theory, one ends up with a Hamiltonian that describes quantum harmonic oscillators, where the coordinates of these oscillators are just the values of the field at some specific points of the space. And depending on the theory you discretize, you just change what stands here for the matrix kappa. For a three-dimensional theory in flat space with a coupling matrix is given by this expression over here. If you are in 2 dimensions, it's a much simpler expression, it's just a discrete derivative, second derivative. Obviously, one writes down the vacuum wave function, which is just Gaussian. Then one considers blocks of this matrix in order to integrate out the environment. And the reduced matrix is written like that, where all these matrices gamma and beta are related to the blocks of this matrix over here. Then Sredniki.
Just to go back to the equation before, there is no dependence on M, right? Just only L.
Yeah, because of the spectral symmetry.
I see, yeah.
That's why we like the spectral tangent surface.
No, you expected it, right?
Yeah.
Do you know the eigenvalues of this matrix?
No, but you can always go to the continuum limit and get the result there if you want to go like that. And in the discrete case, you just know this chain over here because it's top is matrix, all elements are on the diagonals of the edges. I have been trying to solve this discrete problem. I haven't been able to do it. It's very difficult if you have considered this matrix over here.
So for raw values of I and J, it's probably doable.
Yes, difficult. So Sredniki, roughly 30 years ago, solved this problem for us. And you know that the spectrum of the reduced density matrix is thermal and it looks quasi-thermal to be more precise, and it looks like that. Where beta are the values of the matrix gamma, inverse gamma times beta. Okay, so you plug these probabilities in the usual entropy formula, you sum up all the for all the particles in orbit various values of n for each particle, and you get the entanglement entropy. Now, what's kind of making the calculation a little easier is to realize that this matrix gamma minus 1 inverse beta is related to a matrix M, which is just the A block of the inverse of the omega times the A block of the matrix omega. And these two matrices are actually the correlation functions of the value of the field and the moment of the field. So basically, all the calculation boils down to calculating correlation functions in the flat space. Now, moving on to the zeta space, you have the metric that looks like that, where tau is the conformal time, we work with multiple coordinates, and in order to have a canonical kinetic term for the effective action of the field, of the V mode, you have to perform a field definition, and after the field definition, you get an action that looks like a scalar field, but with time-dependent mass term, and the mass term is related obviously to the second derivative alpha double dot over alpha. Now, in this case, you discretize the spatial part just like the flat space. Because I want to end up with an expression that has a momentum here and nothing before in front of the momentum.
Just the scale.
Yeah, to still have the conformal factor. So basically, you did exactly what you do in flat space, but this time.
Sorry. Since you're going to do the calculation at fixed time, why is that important?
With variety time.
Yeah?
We follow the time evolution of this thing.
Okay, diagonal method?
Yeah.
But that will appear in terms of your parameters because the diagonal calculation happens at a fixed time. So all the vacuums will appear at that time, and then we just let them move on.
Yeah, but actually the problem is that if I'm not mistaken, that because there is some kind of conformal symmetry breaking, you end up having contributions that don't cancel this way. Because, for example, as you can see over here, what is over here? The whole calculation boils down to calculating omega minus 1 times omega. If you discretize the system, usually you end up with a large spacing in front of the Hamiltonian, and actually this large spacing is in front of the matrix A, and obviously is proportional to when you do the matrix omega minus 1. So in principle, you can say that the result will be finite when you calculate the entanglement error because the large spacing will drop off. So I can take it to 0 and nothing happens. But if you do the calculation, you end up with having a diverging entanglement entropy. So I guess in a similar mechanism, even though in principle you can think of that you can rescale away the conformal factor, then you can the result will still depend on the value of the conformal factor of the specific time instances.
But you only need one part of the two-point function, right? Not the whole. You get more than what you need.
Yeah, you can restrict the calculation just to your subsystem. So in the Sitter space, you have the factor is given by minus 1 over h tau. And now you have to somehow define the state. You can always perform the same orthogonal transformation that you do in flat space in order to diagonalize all the position-dependent part of the Hamiltonian. And each mode of the system then is subject to this Hamiltonian over here, which is time-dependent. You have to solve this time-dependent Schrödinger equation with the initial condition that for tau goes to minus infinity, you have the ordinary vacuum of the harmonic oscillator without this time-dependent part. Doing so, going back to the original coordinates, not the coordinates of the mode, one ends up with the wave function over here, where the matrix appearing here, the exponent, is symmetric, but is complex. And the fact that this matrix is complex complicates things a lot. The matrix omega appearing here is just a matrix that appears in the flat space calculation. Now you can try to solve this problem the same way as Cernicki did, like calculating the eigenfunctions of the reduced density matrix. And it's kind of messy, but you need a lot of intuition on how to solve the system, but you can do it. And it's kind of more easy to solve the system by considering correlation functions, but this time there are correlation functions high and between the value of the momentum that are not trivial because of the exponent is complex. It turns out that you can prove that both these ways of calculating the entanglement error are equivalent. And what one has to do is to find the eigenvalues of this matrix over here, get the eigenvalues that are larger than 1, and plug them into this formula. All eigenvalues come in pairs of opposite values, so you just take half of the eigenvalues of this matrix over here. The bad thing about this approach is that you have to solve a problem that is 2n times 2n, and not just n by n. This means that it's 4 times more complicated than the flat space case. So when you plug the wave function of the Banzhevich vacuum, you end up with a matrix that looks like that. We are interested in finding the de Sitter correction over the flat space entanglement entropy, so we expand for large values of tau. Now, if you consider the eigenvalue problem of m squared, it turns out that all the powers of tau that appear here are even. Therefore, you can prove that the expansive parameter is 1 over tau squared and not 1 over tau, because here is not manifest when you have the matrix like that. And you can perform perturbation theory and so on and so forth and calculate the correction of the eigenvalue because the factors are in the Sitter space, where the lambda 2 is given by this inner product, normalized over the inner product of the left and right eigenvectors of the flat space problem.
So to get the perturbation parameter is this tau?
Yeah.
So the deceleration is
yeah. Okay, you can write down a formula for contact limit entropy and so on and so forth. You can send this out to the continuum limit, and you, when you consider just the L equal to 0 sector, the vanishing angular momentum sector, and you see that actually, if you consider that the overall system is much larger than subsystems that you are looking to, the result still depends on the size of the overall system. And it depends on aridity. So even though you're considering a small part of the space, somehow the small part of the space knows that the space is finite. And there is this scale over here. So when one has written down all the necessary formulas, you can plug everything in the computer. And one has to take into account these three facts. You have to get rid of finite size corrections, kind of similar to what Alessandro was telling us about. Then you have to sum infinitely many angular momenta, but you can't sum infinitely many angular momenta in practice. And you have to consider the continuum limit, so you have to somehow extract everything that survives when the cutoff is sent to 0.
So these are special slices, right?
Yeah.
But the system has compact slices, doesn't know infinity potential, right?
What do you
We have a flat.
Yeah, but that's not coordinate, doesn't matter. Oh, come on, yes.
It depends
What
on
it is.
the special slice that accept
I mean, the system doesn't have infinity in the special direction. I mean, this is a Hawking analysis.
and extend the future boundary.
This is time-like.
It depends on what time you.
The fact that there's no special slices, the slices in the system are compact, is not a coordinate function.
No, because in coordinates the slices have not.
It's not lasting.
Then you go, but then it's not special slice.
To the future boundary.
That is time-like infinity, it's not special.
You need a space like surface that extends up to the boundary. So you have.
This doesn't exist. This doesn't
It's
exist.
like in ADS.
So basically, one has to perform the numerical calculation, scan over the different values of the size of the system, the size of the subsystem, and different values of tau, sum the contribution for many angular momentum sector. If one tries to do that with mathematical or MATLAB, it can't be done because they are way too slow. We had to write C++ code, and on top of that, we had to use flows of 128 bits that actually correspond to more than 30 significant digits of precision, because we want to capture very subleading contributions. Then one has to see how keeping any small fixed, that's the size of the system, fixed. You have to scan and see how how entanglement behaves when you scale. And so when you consider that the whole system becomes larger, but the subsystem is fixed. In flat space, the finite size correction scale like this. In our case, there is an enhancement, and actually L plus 1 becomes L. And then you can see that you need finitely many angular momentum sector. We think that something like 220 is okay for our precision. And what's going on is that even in the numerical calculation, you can see that the L equals 0 sector the entanglement depends on the size of the system, because you have a term that grows with the size of the overall system. These are some plots that actually calculate some finite differences to see that actually everything scales correctly and according to the formula that I showed you. So keeping only the terms that survive when you take the system to be infinite, you have to extrapolate to the value that you obtain when you add infinitely many angular momenta. So you define some truncated sums and you see how they scale with the cutoff angular momentum. And then finally you are ready to see how entanglement entropy depends on the conformal time and what kind of function of the system size it is. Expanding for tau goes to infinity. You you don't expect a logarithmic divergence in flat space, and actually this is obviously the case when you see the data. So basically, we have enough precision to specify the leading part of the logarithm here, which is goes as 1 over tau squared. The flat space extrapolation of this term over here, and the first decimal correction of this term. In order to be sure that we don't do anything stupid and we actually fit what we're supposed to fit, we consider the L equals 0 separately. We know that the result should be 1 over 6 ln R over E. When we perform an numerical calculation of flat space, we get this number with crazy precision. When we extrapolate the decimal data, we get almost the same precision, specifying the settled charge. And we move on to the calculation of the coefficient of the ln n term, which is this number over here, which is screams that this number is 1 over 3. And actually, when you see the subleading terms, you realize that there is a whole series of this form over here that multiplies ln n. And this is plot that shows these behaviors. You have here the 1 over tau squared that goes quadratic, 1 over tau to the 4 that goes to the power of 4, 6, and so on. Now, you can actually fit the part that does not diverge with n, does not go with n, and we end up with this number over here. You see that this number is actually very close to 1 over 3, and this is a strange number. And hopefully you realize that because we're talking about one-dimensional field theory, you can also solve this problem analytically. And we have done this with relying on some work of mine and George Pastras, where we studied the entanglement entropy in a flat space in one dimension, and we solved this thing analytically using a methodology of Θεωρητική. And when you do this analytical calculation, you end up with this result over here, and you see that this coefficient is exactly 1/3, and the term over here, 4 over 9, is actually very, very close with the numerical value that we get from the fields. They agree to 3 significant cases. Moving on to 3 dimensions, you know from that there is a universal term that's 1 minus 1 over 90. You end up with this value over here if you are in flat space calculation. You extrapolate the jitter, and you get this value over here. And some values over here that are not very significant because we don't know what are the exact values and how to compare them. And so, out of this calculation, we end up with a formula that looks like that. You have the flat space result with this is the famous coefficient that's calculated 1 to 0.3, and this is a more precise value, 1 over 90 over here, and this new logarithmic term that depends on the size of the overall system. So, even more fundamental thing than just talking of this term is that entanglement entropy has a much richer structure that Maldacen and Mendel proposed in their work, because they just have some terms over here, whereas our numerical calculation suggests that there are functions of tau over r or h over rp current physical coordinates.
What is RP?
It's the entanglement in the physical frame. So what we found is that entanglement entropy depends on the size of the overall system. And actually, this is due to we believe that this is due to the fact that the wave function is actually very, at any time is actually a squeeze state, and squeeze state can probe larger part of the Hilbert space than the vacuum wave function of flat space. And what happens is that this phenomenon is kind of analogous to EPR. You have the universe that before it starts expanding, and before the inflation era, you have regions that are totally connected. Then the universe expands, and these regions become totally disconnected. But there is still quantum entanglement between them, and this is why you end up having a dependence on the size of the overall system. And now, for the last 2 or 3 months, we work in AD space, performing similar kind of calculations, and we have seen that actually the de Sitter space calculator is related to the added de Sitter one with this kind of analytic continuation over here. So thanks.
Thank you, Dimitri. Do we have more questions?
Is there anything preventing you from doing the evolution explanation without discretizing entire dimensions?
You have to somehow work with some special functions and some strange things. Kind of the, you have to introduce some exponential doubling or something like that. Huerta has written a paper on the fragment of glass space in arbitrary number of dimensions. When they send angular momenta, they just put like with the hand one exponential doubling factor, and they get artificial linear law like that. But yeah, we can't do anything like that.
Yeah, I was just wondering if you can compare your results to those.
No.
More questions?
Yeah. So when you calculate this, you do this perpetual computation, you went to calculate the one, the first correction?
Yeah, the leading correction.
Eh?
The leading correction.
I didn't.
Yeah.
It's difficult to prove further, no?
Yeah, and basically the point is that if you want to...
Do you know how fast it was done? How small it is?
I have no idea, because at some point you have multiple logarithms, like powers of ln L over tau, and if you see the whole thing as a function and not expanding it, it has some non-perturbative point, and then it switches to a different kind of behavior. So it's, you have to kind of focus in different regimes in order to do it.
During the case of this deceleration, it's very fast, very quick.
Actually, it's at some point you see the evolution of the graviton, it has a peak. And then it kind of drops.
In the interest of time, I suggest, yes, we move to informal discussions after the end of the session. So thank you again, Dimitri. Okay, and I invite the last speaker of the workshop, Giorgos Iliadaris from the University of Ioannina, who will talk to us about fiber inflation in large volume compactification. Go ahead.
Thank you very much for this kind invitation. It's really a pleasure to be here again. So I will talk to you about this topic that we just announced. So more or less the schedule is the following. The main objectives of this talk will be to discuss moduli stabilization and to see how we implement the scenario. Okay, thank you. How we implement the scenario of inflation in string theories. So after some introductory concepts, I will talk about to you for large volume compactifications and inflation. So in string theory, inflation can be driven by specific scalar fields, which we usually call moduli fields. These are associated with the compactification of extra dimensions. At low energy effective theories, we need to stabilize these fields. Otherwise, the gauge couplings on all the parameters of the standard model will not have a definite value, actually. So in order to explain what the issues are, I will just devote a few transparencies in order to explain the reason why we do this. Okay, so let me start with a few facts about cosmology and de Sitter vacua. We all know that there is a major observational discovery some 25 years ago, which tells us that the universe is expanding in an accelerating way. And this phenomenon is explained through the dark energy. We know also that in general relativity equations, dark energy is incorporated through this constant here, a cosmological constant, which is interpreted as the vacuum energy, and this exactly is that what leads the expansion of the universe in an accelerating way. In the context of field theories, for example, you can describe this thing, this potential, through a potential energy from, for a field, a scalar field, which exhibits a minimum. Here is the cosmological constant in the minimum, and this could be metastable, and this is what we call the Sitter vacuum, actually. If we have a potential with a few more requirements than the ones that we described, then we can also accommodate this cosmological inflation. And we know also that there are numerous effective models that can be constructed and successfully satisfy these constraints. But the main challenge here is how to implement this scenario in a viable string model. So I will just tell you how these novel ways work in string theory. Even if we manage to implement this scenario, we have several issues in an effective theory which comes from strings. And as I mentioned earlier, there are moduli fields which must be stabilized. In general, the deformations of the compactifications lead to massless scalar fields in the effective theory. And if we cannot give masses to them, then we have problems with fifth forces and other cosmological issues. So the tasks now are to, in this context, of course, first to generate a potential, to assure positive mass square for all the moduli fields. This is the so-called project moduli stabilization. And the second one is, once we have obtained this stabilization, to search for a possible inflaton candidate among these moduli. I will talk to you for models, inflationary scenarios that apply to these type 2B string theory scenarios, and actually to the large volume compactifications, as the title of the talk is. So before I go into the details, let me just in brief present the notation of the fields that we are going to use in this talk. First of all, we know that we have the dilaton field, which is related to the string coupling in this way. We have also the P-form potentials. P is even here for type 2B. And through them, also in the Kalb-Ramond field, we define the field strengths that you see here in this way. Here, these two things contain two scalars. One is the dilaton, the other one is the C0 potential, the action field is. So we combine these two in this complex combination, the axiodilaton modulus, which is instrumental in constructing type 2B theory and the action actually with all these modular properties that we know. Finally, this is the notation that I'm going to use for the complex structure moduli. We know that these are related somehow to the shape of the compactification space. And also the Keller moduli, I will use this letter T, which are related to the size of the moduli fields, of the compactification space. I will use this notation. So here is the component that we will use often in what follows. Yes.
These are oriented, right?
Yes, that's right. That's right. That's right. Yes. Okay, so let me now just describe the potentials of the theory. So the low energy dynamics can be captured by the holomorphic superpotential and the Keller potential, at least the things that we're going to work here. Okay, first of all, we rely on this definition of the superpotential, the tree-level potential, the Gogov-Vafa-Witten. We will see this many times. And actually, this is formed by the combination of the field strengths that we have just seen and the axiodilaton that we defined, and also the holomorphic three form, which depends on the complex structure moduli. So what we have here is a tree-level superpotential, which depends on the complex structure and the axiodilaton. That's it. The second ingredient that we have is the Keller potential, which depends logarithmically on the axiodilaton complex structure moduli, and in addition here also it depends on the Keller moduli fields, something that is not present in the superpotential at tree level. That's important for the rest of the discussion. Okay, having defined this, now we can go to the F-term potential. We can construct it using a standard supergravity formula, which is the low energy limit of this theory here. So the formula is the derivatives, the covariant derivatives on the superpotential, the Keller metric, and this exponent here that you see.
So mu is still tree-level, right?
That's right, yes.
And
Yeah.
that comes from non-trivial alpha prime corrections, is that?
You will see them now. Okay. Okay, let me now go and describe the fiber inflation. So I will describe two basic approaches, non-perturbative and perturbative. And I will tell you about merits and demerits about these two cases. So let me start in brief with non-perturbative moduli stabilization and slow roll inflation. These things are already there in the literature. We have just contributed only to the part of the perturbative one. So let me in brief describe what happens here. Okay, moduli stabilization in type 2B theory can be usually follows two-step approach. The first one is that one fixes first the complex structure moduli and the axion dilaton by the leading order superpotential that we have already described. And this, as we've seen, depends on the fluxes which are related to these field strengths. Because of the no-scale structure of the theory, the Keller moduli remain at this level massless, and which means we cannot stabilize the things up to now. And this is exactly what we need to do, is to go to the second step where these Keller moduli can be stabilized by alpha prime corrections and non-perturbative corrections to the superpotential. Schematically, I write here the non-perturbative corrections as a function of the axiodilaton and the Keller moduli, and also the contribution of the alpha prime corrections will come here. We'll replace this U, the volume, to account also for the alpha prime corrections and other corrections that I will describe next to it. Okay, so how these fiber inflation models work. There is a basic geometric setup that one has to set up, and these are the D-branes. We have D3 branes, D7 branes, and the corresponding O7 and O3 planes. And also, the second ingredient is that the volume has a specific form, the so-called Swiss cheese form, just because of this minus here. There are two parts. The first part is a degree 3½ homogeneous function of the blue moduli. These are what we call a large Keller moduli, or in this string jargon, say, divisors. We just have NL of them, say. And also the second part here is a sum over all the small blow-up rigid divisors. The sum of all of this, of course, has to be equal to the Hodge number, which accounts for the 1-1 harmonic forms. Okay, once we have all this, now let's go to the quantum corrections. Quantum corrections now to the superpotential that we have already seen are only non-perturbative because, you know, the various normalization theorems prevent other three-level contributions to this potential. Okay, so the non-perturbative contributions to this have to be through only rigid ones. Otherwise, it's not possible. Some rigid divisors, we know it's Del Pezzo divisors, for example, or those which are fixed by fluxes. Anyway, assuming that this is the case, as the red part of the volume, as we have seen, contains these scalar moduli, the blow-up moduli, which enter here into this correction through this exponential expression that you see. These corrections are generated in general either by de Bruijn instants or gauge-Genon condensation. The coefficients here in general depend on the complex structure moduli, but in the first step of moduli stabilization, we have already taken care of them, so we can consider them as constants. Okay, now the Keller potential. In the Keller potential, long time ago, we have seen papers where, oh, sorry, where is this? Yeah, we are here. So we have seen papers where these things have been accurately calculated, and actually what happens is that these corrections are proportional to the Euler characteristic of the manifold. So these corrections enter through this quantity xi here, as you see, and they shift actually the volume by this quantity here for some other reason that I cannot explain now. You also see here the gauge coupling, the string coupling. So this function u now replaces into the Keller potential the volume, so that's why I write here Keller corrections, alpha prime corrections. So, okay, these are the first corrections that one has. So we have now the following steps. We fix with these corrections the overall volume and the small moduli, the blow-up moduli. And if we fix these things, then we are left with NL minus 1. Remember, NL is the large moduli, which are unfixed. Minus 1 here because also the volume, which is a combination of all them, is subtracted. So in the theory, in this first step, we have NL minus 1 natural inflaton candidates. At the second step, there are subleading terms that I will describe later, which depend on the string expansion parameter, of course. And these are of KK exchange or winding modes, which fix the remaining degrees of freedom. But because they are subleading, one expects that the contributions to the scalar potential are flatter, so that means we can have slower inflation with this or some of these moduli fields. Okay, so here is a simple example which appeared in this paper. We have a model with 3 Keller moduli. Here are the corresponding bases of the divisor bases. Here ds is a diagonal blow-up divisor in the sense that it does not intersect with the rest. So the volume that you see here is just a simplification of the previous one, just for 3 Keller moduli with one divisor, which is rigid. This means that we have only one correction here in the superpotential, one divisor which is small, one correction, and this is the superpotential for this simple model. Now with the loop effects, which are the ones that we described, we have contributions in the superpotential. If you count now how many fields we have, according to the previous description, we have fixed. In the first stage, we have fixed the volume, which is one combination of this, and we have also fixed this small divisor, which means from the 3 ones, we are left only with one. And this should be the inflaton field. Okay, that's the picture. Okay, however, we are not done yet. The problem is that the Keller moduli space must be such that ensures a positive definite Keller form. But this puts very strong corrections. In fact, in this model that we described, just because of the appearance of the small moduli, of the blow-up moduli, you have to impose severe constraints, which means it restricts the range of of the inflaton field into this bound. But of course, if one checks the slow roll inflation, one sees that one needs something like this in order to have enough plateau to realize the foldings in his model. Which means we have to go to a very contrived model if we want to accommodate a realistic inflationary model in the non-perturbative case. So that contrived, I mean, okay, you have to go to your parameter space in some corner, which you fine-tune.
That would mean that you cannot use this effective action too, because the condition for chain positive means that you can trust your geometry. Trust your geometry, you don't trust
That's correct. Okay, what I'm saying is the following, that you have to trust the condition, which is the Keller-Kohn condition, which means from your parameter space, you have to put so much constraints, or you have to assume so small constants undetermined by your theory in this sense. Yes, which means fine-tuning. Okay, that's why we thought it's a good idea just to see if we go to some perturbative contributions of instead of non-perturbative, if you can evade these constraints. Okay, so the idea is then to use only perturbative corrections and dispense with the use somehow with non-perturbative contributions, which create the big problem in this model. So the rigid divisor in this approach that we discussed and creates the problems will not appear, which means these Keller-Kohn conditions will be relaxed somehow. They will not put a severe bound. Okay, so we work in a model where we demonstrate all this in a model where we have a K3 fibered Calabi-Yau manifold with toroidal-like volume. Okay, so let me just describe in brief. Describe in brief a global model. So the global model that we searched in a basis that you can find in this old paper here is the number 249, if you are interested to see, is one model which has 3 Keller moduli. So the Hodge numbers of the model is H21, which is the complex ones, 115, and 3, as we said, for the Keller moduli. Actually, this is okay in the sense that the Euler characteristic that you compute from this is negative. This is essential because this is the way if you wish to obtain a minimum in the F-term potential. Okay, then you compute, you write down, your Keller form, you compute the volume, and the volume you see that has a very simple toroidal type form. And if you apply the Keller-Kohn conditions in this case, they are very simple and very natural. The only thing, recall that these are the Ti are the 2-cycle Keller moduli, and the tau I are the 4-cycle moduli. So the Keller-Kohn conditions are very simple. They just require to be positive, all these things. Okay, so the global model that we have, among other things, predicts subleading corrections of the following type. Because we have 3 D7 branes in this model, D brane stacks actually, okay, and because they intersect on T2, which is non-spherical, this means that we have winding modes around the tori, and this means we have string loop corrections of this type. We don't have other corrections, just because we don't have, for example, parallel branes in this model. So I briefly show you here the scalar potential that one obtains. Let me explain that the first contribution here contains an uplifting term, which comes from D-term contributions to the scalar potential. It contains the logarithm of the volume, which are perturbative corrections, and these fix the volume actually. Together with the rest here, you fix another Keller modulus at the high scale, and there remains one modulus of the 3, which somehow is light, and then you can express, thank you very much, and then you can express your scalar potential in terms of this modulus. It's one of them, one combination of them, which you call this tau f, and this can drive inflation. So that was the basic idea. Only perturbative corrections. The superpotential is exactly the three-level potential that we saw, the Gukov-Vafa-Witten superpotential. Okay, so now in order to go to inflationary dynamics, we have to define the canonically normalized fields. The canonically normalized fields, it can be seen that it's just the logarithms of the Keller moduli, the imaginary part actually. So we can write the volume in this exponential form, and then in the large volume limit, you can simplify the previous formula to write it in terms of only these 5 terms. So here, these R0, R1, and R2 are constants, and the required uplift in order to have a de Sitter space is this one, which means what you have to do is just to fix a few of your parameters that enter in the D-term contribution, and we don't know them exactly, but you have to fix them so that you obtain this value which produces a de Sitter space. I should tell you that in this model, because of the structure, we don't have all 3 planes and we don't have D3 bar uplift contributions. This contribution was in the KKLT model introduced. In my opinion, there is a lot of discussion about the validity of this D3 bar. We have already listened to several talks about this thing, so I'm not discussing it. What we do, we just use deep brain uplift, which has appeared also in this paper, in order to uplift the potential and obtain a constant C-up, which is the required one in order to uplift the potential to the de Sitter value. Okay, here what we see is that we choose some coefficients within the validity of the range of the parameters, but still are small, I should admit this, but not so much fine-tuned as in the non-perturbative case, which gives us correct somehow, in the correct range, these values that we expect. For example, the string coupling is something like 0.3, which is in the perturbative region, and the volume is some 1,000 and more, which is enough to validate the large volume expansion of our theory. So the potential looks like this. There is a plateau here for at least some of the values that we use, and here you can gain all the e-folds that you need. And the parameters that we obtain in the cosmological side is the e-folds is, for some of these models, around to 78. The scalar perturbation amplitude is something 10 to minus 9 as expected, and also the spectral index is this one that you see within the accepted range that it is suggested by cosmological data. And here, for some reason, I don't know why this is in front and the other in the back anyway. Here, these lines are for various values of the coefficients that you have seen here in the previous page, which means we have a small ratio R. Okay, let me now go to the conclusions. In this talk, I have discussed fiber inflation in large volume compactifications. So what we have seen that the perturbative corrections do not require rigid divisors and do not have strong constraints from the Keller-Kohn constraints. And thank you very much. And this was instrumental somehow to construct a robust string scenario with fiber inflation. So the model has a global embedding, as we discussed in the last few pages, and the minimal Keller of the moduli are able to accommodate inflation. We just need only one in this model, and the volume has this very simple form. So thank you for your attention.
Thank you very much. But your goal also for finishing even before, yes.
Yeah, because there's something that follows.
Yes, exactly. So
Why is this called fiber?
It's fiber. It's somehow these moduli fields. This is what I understand at least. These moduli, the Keller moduli, look like a fiber in K3 space. So usually, what you have in these models, you have either volume inflation, yes, or this kind of inflation with a specific construction of the volume, which is called fiber inflation.
The total volume doesn't run here.
The total, no, is fixed at large value, the total volume. You can use another approach and use the volume.
Okay,
Yes, okay.
more questions? I think you raised your hand first. So just first come, first serve.
From the parameters you presented, which is the most important to get the correct result for inflation?
These blue ones.
Yeah,
Yeah.
blue one.
Yes, these blue ones. We have to suppress somehow. You know, the problem is the following. We started in the beginning with, in the old days, with corrections that we discovered of this type. Right. If you want, I can give you more information. So, as Elias pointed out, there is also the possibility of using the volume in order to inflation. When you stop to these corrections, then the volume plays a decisive role in your results, and you don't have to add the rest of the subleading corrections. Yeah, now the thought was that we should also take into account corrections that other people have done. In the beginning, we didn't do it. So we were led into this picture of fiber inflation, where we added these corrections through this R1 and R2. And then we discovered that the only way for fiber inflation to work is to suppress somehow these corrections into acceptable range. Not that much as in the case of non-perturbative corrections, but even here we have to suppress somehow. So it was, instrumental in our model to have small values for these things, but still acceptable. Okay, the work continues. We hope that we will find something better in the future, but this is what we have done up to now.
Yeah, we heard a lot about Swabland this
This is excluded.
Huh?
This is excluded by Swabland.
Yeah, so that's the question. Is this a counterexample to is this a counterexample to the Swabland notice string theory conjecture? And if
No, it's
not,
Yes.
They don't like these things.
yeah, but
Yes,
why?
that's right. It's
This is a Planckian. It's the this value of phi, which is let's say 5-6 months Planck. It's not good for them.
The Transplanckian one.
no. Please go on. No. Go on, because I will reply very. It's a model against swampland. In other words, it's a correct model in wrong times.
Do we have still any Swabland person here? What would Vafa say?
Well, Vafa. Okay, I'll tell you what Vafa said. Maybe 2 years ago, I organized a conference in Ioannina. It was this supersymmetry conference, and Vafa was one of the participants and speakers. And when our collaborator presented this model, is Osman Lacombe with Ignatius Antoniadis. Vafa objected the approach. Ignatius insisted, and then Vafa said, okay, you should call it a scenario and not a model. And after that, I call it scenario. So that's the story. Yeah. Anyway. Yeah.
Yeah, let's take one last question since we finished early.
What is the scale of inflation in this type of scenario?
It's a large field inflation. If you go to the volume, you have the scale around the gut scale, which is nice. But for these ones, you have seen that you exceed the Planck scale for this. Yeah.
How many orders?
Well, less than 1 order. Yeah. You see this value phi is just the value of the field in Planck units.
Are all moduli stabilized?
Yes, that's right. We have, look, okay, that's a tricky question. for the following reason. You have complex structure moduli and you have Keller moduli. All the Keller moduli are fixed. However, complex structure is not an open, is still an open question, because you consider at the first